an important and useful result that comes out of working with bases is particularly if we want to span Rn for some value n, it requires n linearly independent vectors to do it. It's just one of those useful things to know. So, for example, if we were to take R3, we have our familiar ijk coordinates, and in this class we've been using this E1, E2, E3 to denote the unit vectors in each of our three x, y, and z directions. So these three vectors will in fact span all of R3. In other words, we can generate any vector within R3 using these three. And again, as long as we have three linearly independent vectors in R3, then that will suffice as a basis for R3. So we can use an example that's different than E1, E2, and E3 to illustrate this. So we take U1, I'll have equal to 1 minus 1, 0, and U2, which is minus 2, 3, 1, and I'll have a third vector here again in R3. That one's going to be 1, 2, 4. So to answer whether or not this particular set of vectors spans all of R3 and in fact will then serve as a basis for R3, we need to check two things: that the set of vectors is linearly independent, and that any vector in R3 can be written as a linear combination of these vectors. So what that means is that A times X equals any vector B, and that is always consistent. For any B in R3. Kind of worked with this kind of stuff before a little bit. So to check the first part of this question, we can simply verify that the matrix is made from a column of vectors that is row equivalent to I3, so the identity matrix in R3. And for the second question, we have to verify this other statement that AX equals B is always consistent for any B. So let's look at the augmented matrix we get when we put in our vectors. And as we've typically done in the past, to determine range, we'll throw in the vectors B1, or the scalars B1, B2, and B3 on the end here for our constants. And then we would go through the row ref process here. And although I haven't solved the entire thing out, the important part is done. So we would get a result here, and it turns out that in the bottom we just get B3. Since the bottom row is not all zeros, we can say that this system is always consistent, and therefore the vectors are a minimum spanning set for R3, and as such, a basis for R3. So what we got here, again, on the left-hand side is row equivalent to I, which would tell us that the vectors we started with are linearly independent. And now we have three linearly independent vectors in R3. And what we see happening then when we solve for the range is that the last statement here says that this is essentially always consistent, and therefore then this would span all of R3. Since we initially showed that the row reduction process produces the identity matrix, again being the left-hand side of this matrix, it should be clear that as long as the three vectors are linearly independent, this will result in a system that is always consistent. Again, noting the bottom row would always be consistent for three linearly independent vectors in this size space, and effectively proves that any three linearly independent vectors in R3 will serve as a basis for R3. So Now we have that E1, E2, and E3 are a basis for R3, but now we can also choose maybe these three as a basis for R3. In fact, there's a lot of things that will serve as a basis for all of R3. So I've got another example here that I'll have you guys work through, and we'll just go ahead and verify the set of vectors is a basis for R3. And I'll also have you determine the coordinates. For the vector B with respect to the basis. So here's our set of vectors. U1 is going to be equal to 1, 0, 0. U2 is going to be equal to 1, 1, 0. And U3 is going to be equal to 1, 1, 1. And we'll take this vector B in R3 to be 3, 5, minus 1. And we can actually answer both of these questions at the same time by entering the vectors into an augmented matrix and row reducing it. What we hope to see is that the left-hand side of the matrix reduces the identity matrix. That would indicate to us that these three vectors are linearly independent, and therefore, three linearly independent vectors in R3 would serve as a basis. The right side of the matrix will then be constants that serve as the coordinates for the vector B that we were after. Note that if the left side of the matrix does not reduce to I, then the vectors are linearly dependent and thus do not form a basis for R3. So I'll have you guys work through that and see if you can determine what those coordinates are.